In this video, I'm going to be covering some of the material from chapter 30. So the idea here is that changing magnetic fields induce current. So let's imagine we have this wire just forming a little loop like this. And at the beginning, there's no current going through it because there's no source of EMF, right? Like it's just a wire in a square here. Now, if we were to put it in this uniform magnetic field, nothing would happen. But if we were to have this magnetic field changing in such a way, or specifically, if we were to have the flux going through this loop to change with respect to time, then a current would be induced inside of this wire. This is mathematically represented by this. So here it says the induced EMF in a loop of wire relates to the changing magnetic flux E, so E is the EMF, is equal to negative. This is known as Lenz's law, like the negative sign itself, and we're going to talk about that later. But then we have the derivative of the flux with respect to time, where here, hopefully you remember, the magnetic flux is just defined as literally how many field lines do we have going through this square here. So here we have like this closed loop integral, because it has to be a closed loop. And then we have dA, which is the area components, and then B, the magnetic field. So then we just take that, plug that in here, and that tells us what the induced EMF is. Now, if we were to have this closed loop here being composed of like multiple wires, forming like multiple loops around it, then we just multiply it by n here. We've seen this a couple times before. So what we see is that we can induce an EMF by changing any of these components with respect to time. So for instance, if B, the magnetic field, so its magnitude changes with time, that gives us an EMF. If A, the area of our loop, if we're changing this, how big this is with respect to time, that changes, or that induces an EMF. Or if we change the angle between B and A, that is also going to induce an EMF here. We're going to talk about something a little bit different now. It's called emotional EMF. So here, we're going to keep B, the magnetic field, uniform. So this is B. It's going into the page. I didn't draw it everywhere, but just think of it as going into the page uniformly at every point in space here. What we see is that by moving a conductor within this magnetic field, that in and of itself induces an EMF inside the conductor. So of course the EMF that's induced is called emotional EMF, right? Because it's because of the motion of the conductor inside of the magnetic field. So here a conductor has length L and it is moving with velocity v to the right. We know that because we have this motion inside this magnetic field, our charges are going to experience a magnetic force like this, so QV cross B. So if we have a negative particle, we can use a right-hand rule and we see that it is going to be pulling it downwards. You do have to be careful here because normally the right-hand rule is used for positive charges. So if you do it, you get an upwards direction, but here, because it's negative, you flip that and FB is going downwards. So because we have this force pulling all these negative charges down, the negative charges will start accumulating here and the positive charges will start accumulating here, right? So that's what we see here. And then we have kind of this like distribution of charges like we've seen with capacitors. So because we have positive here, negative here, we have this potential difference between them. And we also have this electric field. Because there's this electric field, our negative charge is going to experience an electric force in the opposite direction. Now we know that at some point FB and FE are going to balance each other out, and that's going to happen when, well, they're equal to one another, right? So FE is Q times E, FB is QVB, because here, if we look at it, we know that B is perpendicular to V, so then the cross product goes away, and then we just have QV times B, like this. Get rid of the Q's, and then we get E is equal to V times V. The question could be then, at what potential do we reach equilibrium? Right, so we know that delta V, the potential difference between these 2 points, is just E, the electric field, times the distance separating our charges. That's from our capacitors lessons. So we get delta V is equal to E times L, because in this case, the distance here, that is L, right? So then we just get E is equal to V times B, bring it over here, and we get delta V is equal to BL times V. This is not super interesting in and of itself because nothing can really happen. Like, sure, we have this delta V, which is in essence like what we had when we had batteries, but it's just kind of like a battery sitting by itself. It gets interesting when you connect this battery to a circuit, and that's what we see here. It's the exact same setup. So here we have a bar of length L sliding across parallel conducting rails. So this is a conducting rail. We also have a conducting wire that has a resistance R here. This is what we had before. This is our conductor, right? And it's moving with a velocity to the right like we had before. And we can think of it as having this like applied force that's like pulling it to the right because something is making it move. And we just call that F applied. We have this magnetic field going into the page literally everywhere along here. And then the exact same thing that we saw here applies. So the separation of the charges, right? So here the electrons in the bar are moving in the magnetic field, like so. They experience a magnetic force, creates a potential difference. The bar acts as a source of EMF and then causes electrons to flow. Because when we have a battery like this, electrons are then going to be able to flow within the rest of the circuit. The question could then be, okay, well, what is the EMF, right? So we know that here we have the flux is equal to B times A. The reason for that, if we go all the way back here, this is your definition for flux. We have a very, very simple geometry where we just have the magnetic field coming like this, and then we have the area that's literally in the same plane. So then we don't have to integrate because nothing's different. It's all the same everywhere. We have this uniform field, and then we can just take B out and then multiply that by the area. What is the area? The area depends on where this conducting like chunk is, right? Because if it's down here, the area that's enclosed by the circuit is this region. So it's all of this. So we're going to call X the distance from here to where this conductor is. So that's X. Then we say that the flux is equal to B times L times X. Where X again is just the position of the bar. What we see is that E, the EMF that's induced here, is equal to negative d phi over dt. So then we have negative d over dt. This is 5b. And then the only thing that's changing with time is x, because that's a position. We know that at some later point in time, because it's moving with this velocity, maybe it's going to be way down here, right? So then we know that dx over dt, that's just the velocity. So we say that E, the EMF, is equal to negative b times L times v. So what this is saying here is that we are going to have this current flowing through our circuit here, where this is our EMF of magnitude b times L times v, and we are going to have our positive charges moving in this counterclockwise direction. We can then say, okay, well, we know there's like a V, an EMF, so what is the magnitude of the current? We know I is equal to V over R, or here E over R, and so that's equal to B times L times V, because we're just looking at the magnitude, divided by R. Now the tricky thing comes in here, not tricky, but it's more just like another layer of things happening, because we now have these charges moving inside of this wire, like this. And we know that moving charges create magnetic fields. So then if we think of it and use our second right-hand rule, we have I in this direction, and that's going to induce this new magnetic field that's going like this. So into the page here, out of the page on this side. So these are new, right? So originally we just had this into the page magnetic field everywhere, but now because of this EMF that's been induced, we have this current. This current is then going to induce a new magnetic field here. So because of the current now flowing through the bar, there's a new magnetic force opposing F applied. Or because we have this new magnetic field, so there's going to be a new magnetic force, another magnetic force that is experienced here. So what we see is that here, this is the original magnetic field, those little X's. And we now have this new current going in this direction. So it's going like this and then up like this. So this is the current. And we know that the magnetic field on a current carrying wire is IL cross B, where L is in this direction. And so we get ILB because, of course, they're perpendicular to one another, and then we just plug in what we know. So this is I, BLV over R, which is here, times L times B. So then FB is equal to this, and it's going to be in this direction here if we use our right-hand rule again. So what we see is that we now have another magnetic field, or magnetic force, sorry, that is opposing this applied force. This is all a little bit complicated because there's a lot of stuff going on, so I'm just going to recap briefly. Originally, we just have this conductor, right? The only thing we're making this conductor do is move, and it's moving to the right with a certain velocity. And it's moving inside of this magnetic field that is everywhere. Because of this motion in the magnetic field, what we saw is that our negative charges pile up here, positive charges pile up here. Because we have this pile up, we can essentially say that this is acting like an EMF because of this change in flux here. So we have this EMF, and this is then going to give us a current that's going through the circuit, and then this current is going to induce another magnetic field here that's going to be a little bit different, because here it's going to be pointing out of the page as compared to the original one that's pointing into the page, right? So if you remember at the beginning of the video, I talked about how in Faraday's law, there's that negative sign. So it's negative change in the flux. That's really important. The idea here is that the induced current in the loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area closed by the loop. Again, a little bit weird, but here, the idea is we have this magnetic field here, right? Whenever, and I should remind you that this is everywhere. So we have these X's literally all throughout this paper here. These are the magnetic fields. Whenever we're moving this conductor to the right, we're essentially opening up our region. So this region that's enclosed here gets bigger. Because that region gets bigger, we have more field lines within the region, and those field lines are all pointing into the page. So the idea is that the current that is then going to be induced by this whole situation has to be such that it opposes that magnetic field. So here we have an increase in magnetic field going into the page. To oppose that, we need to have magnetic field coming out of the page. The idea here is that we don't want, the system doesn't want the flux to change. The flux is changing because we're moving this bar here, but to oppose that change, because it does not want to change, it's going to give us a magnetic field in that opposite direction within this region here. So again here, as the bar moves to the right, the area increases, so the flux increases. The current creates out of page B to counteract that change. We can think of it as, we can also think of it in this scenario where here we have this area closing. Because that area is closing, we get less of these magnetic field lines within that area. To compensate for that, the current is going to be such that it gives us more into the page magnetic field lines. So again, the area, because the area is decreasing, the flux is decreasing, so the current creates a magnetic field into the page to compensate. We're going to go over a couple of problems a little bit later on, but I do recommend reading the textbook for this one.